Good afternoon. This class is for my grade 9s who are at home right now, but this is obviously introductory chemistry for anybody who is learning the makeup of the elements. The homework was the even numbered questions in the picture of the textbook that I will add to the site. It's not up yet, but it will be in the next hour or so. Here is the answer to 48. And I'll show you the rationale as to how we answer the question. So at the top of this particular table, they've put in several pieces of information, but they've left many others blank. In this first row, all these were blank, but this information was here. So I looked up arsenic on the periodic table, and I saw that it was element 33, which right away tells you that there are 33 protons, because this number is dedicated to telling us how many protons are in the element. This number tells us how many protons plus neutrons. This section of the atomic symbol is reserved for telling us the charge on the element, and this space next to the element symbol is reserved for telling us how many of the element are present. So there's 33 protons. And if we subtract 33 from the 75, we get how many neutrons there are, which turns out to be 42 in this case. For the arsenic atom to have a -3 charge, it has to have a surplus of 3 electrons. Since it has 33 protons, a surplus of 3 electrons would mean that it has to have 36 electrons, and that's what we have here. So the net charge is -3. The second example, they don't have this part of information, but they've put in these 3. So if you add protons plus neutrons, you can get this number, which is 59. 28 is given here, it's the number of protons. And it says there are 26 electrons. So if there's 26 electrons but 28 protons, it means it's going to have a +2 charge. In the third example, they gave you this number, and the charge. So they didn't give you the number of electrons, but because they give you the number of protons, you can write it here in the space next to the atom with the atomic number 53, means it's iodine. And because the iodine has 54, because it has a -1 charge, it must have 1 electron more than it does protons, and that's why we can write down that it has 54 electrons. And then if you add these two numbers together, you get the mass number. 53 plus 74 gives you 127. In the last example, they gave you these 3 numbers, but not these 2. So if you add so if you're told you have 76 electrons and the thing has a +3 charge, that means that it has 3 more protons than that. So 76 plus 3 gives you 79. 79 is the atomic number for gold. So our element is gold, and then once we know that this number is 79, then this has to be 79 because that's the number of protons. 79 plus 118 gives you the mass number, which is 197, and then of course the charge is +3 as it was written below. So again, to recap, on the element symbol, the bottom left corner is reserved for telling us the atomic number, which tells us the number of protons in the element, and which gives the element its identity. The element is, the periodic table is arranged numerically, starting from 1 at the top left, which is hydrogen, then it goes across to helium, and then you read it like a paragraph, 1, 2, 3, 4, 5, 6, 7, and that's how the atomic numbers increase as you go across, as though you were reading the periodic table. And as each number increases by 1, you have one more proton, and the nucleus of the atom gets increasingly larger. And usually associated with a certain number of protons, you'll also have some neutrons which tend to stabilize the nucleus. The more protons there are, the more neutrons are necessary to maintain a stable nucleus. And so you'll see the nucleus number increasing somewhat linearly with respect to the proton number. There's obviously some variation, and that's how we get isotopes, because there are elements that are known to have variable numbers of protons. Carbon, for instance, can have anywhere from 6 to I think, 9 neutrons. The most commonly known varieties are 6, 7, and 8 neutrons. So you have carbon 12, carbon 13, and carbon 14 are the most common isotopes of carbon. Let me see if the periodic table has any other isotopes that I don't know about. Carbon 14 is the biggest one I see here. Okay, and this number is the number of protons plus neutrons, and this is the charge that's on the element. And the way you can find the charge is if you know the number of protons, it will have an equal number of electrons if it has a neutral charge. If it has a charge that's not neutral, then if it's a positive charge, then that means you have fewer electrons than the number of protons. If it has a negative charge, it means you have extra electrons as compared to the number of protons. And lastly, this space at the bottom right of the element symbol is reserved for telling us how many of the element there are. So for example, when you write H2O, H2O means that there are 2 hydrogen atoms and has nothing to do with the oxygen. There's only, because you've written at the bottom right, that number 2 signifies there are 2 hydrogen atoms, and you never write 1. If it's H2O, you just leave it without writing the 1 because the 1 is understood. The next question we did was 250, and it says in the question, use the periodic table, predict the charges of the ions for the following elements: strontium, scandium, phosphorus, iodide, and selenium. So strontium is in group 2 metal, which means it has to lose 2 electrons to acquire a stable octet. And by stable octet, we mean a configuration that resembles the electron configuration of elements that appear in group 18 of the periodic table. So whenever an element takes on a charge, it will take on a charge that will allow it to resemble the closest, and by closest I mean the noble gas that has the closest atomic number to itself. So it might be on the opposite side of the periodic table, like strontium, but if strontium loses 2 electrons, it will become isoelectronic with argon. So strontium normally has, sorry, not argon, krypton. Strontium normally has 38 electrons, but it loses 2 of them, and then it will have 36 electrons. When strontium has 36 electrons, it has the same electron configuration as krypton, so that's why it's called isoelectronic with krypton, and it'll have the same stable octet as krypton, and that's why strontium with a +2 charge is a stable cation. Scandium is in group 3, so it likes to lose 3 electrons and becomes isoelectronic with, again, with the krypton, if I'm not mistaken. No, it becomes isoelectronic with argon. Just going to keep a periodic table handy here, so let me show you how that works. So here's strontium. It'll lose 2 electrons to become isoelectronic with krypton. Scandium is here, and it'll lose 3 electrons to become isoelectronic with argon. So it's on the opposite side of the periodic table, but it's very close in atomic number. So scandium has an atomic number of 21, and argon has an atomic number of 18. So it only has to lose 3 electrons to be isoelectronic with argon. That's what I mean by it being close to the closest, resembling the closest noble gas in electron configuration. Phosphorus will gain 3 electrons to become isoelectronic with argon. So phosphorus is here, and it'll gain 3 electrons to become isoelectronic with argon. And that's why a stable phosphide ion will have a -3 charge. Now let's move on to the top of the next board. Iodine will become iodide, and by becoming isoelectronic with the closest noble gas in that case, which is xenon. So it'll gain 1 electron to become like xenon and acquire an octet. Selenium will gain 2 electrons to become isoelectronic with krypton. So we see selenium is here, and it gains 2 electrons, and it becomes isoelectronic with krypton, again, so that it can acquire that stable octet. And in so doing, it acquires a -2 charge. Question 252, they ask, the most common charge associated with silver in its compounds is +1. Indicate the chemical formulas you would expect for compounds formed between silver and iodine, sulfur, and fluorine. So if you have silver here with a +1 charge, it'll form an ionic compound with iodide to give you silver iodide. If you have silver forming a compound with sulfur, it's a mineral with its own name. It's called acanthite, if I'm not mistaken. Silver with a +1 charge, it'll require 2 silver atoms to form the sulfide with a -2 charge, so that when it forms the compound, it's neutral. And then finally, silver with fluorine will form silver fluoride, 1 of each, because the silver is +1 and fluoride's -1, so you get 1 of each to form the ionic compound. 254, predict the chemical formulas of the compounds formed by the following pairs of ions. The way to figure out what the formula of the ionic compound that results is some people call it the crossover method. So you take whatever the charge is on this side, this is 1, and you put it on the bottom of the other side. Here it's 2, so you put the 2 over there, and you get the formula for your ionic compound. So cuprous sulfide is Cu2S. How did I know it was called cuprous? Because copper forms 2 possible ions, +1 or a +2. The +1 is called cuprous, the +2 is called cupric. So in this case, we have the cuprous form of copper combining with sulfur, and then you need 2 of them because you have to have a neutral compound at the end. Iron with a +3 charge is ferric, and it's combining with oxide, which is -2. So again, cross over if you like and get Fe2O3, that's called ferric oxide. Mercury sometimes forms these diatomic ions with a +2 charge. What happens here is the mercury is sharing that +2 charge. So basically what that means is each mercury atom has a +1 charge, and the diatomic ion has a total charge of +2. So mercury is I think the only one that does that peculiar thing of making a diatomic ion that I know of anyway. And so the +2 with the -2 gives you Hg2 with CO3 with a -2 charge, so 1 of each. And what you get is mercurous carbonate. So in this case, mercury can have a mercurous with a +1 charge on each mercury atom, or you can have 1 mercury atom with a +2 charge, and in that case would be called mercuric. So if it was just a single mercury atom with the carbonate, then you would call it mercuric carbonate. And D, you have calcium ion combining with arsenate. So you're going to need 3 calcium ions to have the same amount of positive charge as will be produced by, you're going to need 2 arsenate anions to have as much negative charge as 3 calcium cations. So the formula ends up being Ca3 and AsO4 taken twice. That's why I put a bracket around the arsenate anion, and then I put a 2 outside of it. And at the end, the ionic compound shouldn't have a charge. And that would be called calcium arsenate. Example E, we have ammonium ion, which is a +1 charge, combining with carbonate, which is -2. So you're going to put a bracket around ammonium and put a 2 outside to show that 2 ammonium ions have to combine with 1 carbonate anion, and what you get is ammonium carbonate. In exercise 256, it says, which of the following are ionic and which are molecular? The good rule of thumb to help you decide is the further apart they are on the periodic table, the higher the chance it is going to be an ionic compound. And if 2 elements are found close together on the periodic table, they tend to be molecular. So in this case, PF5, the phosphorus and the fluorine are close enough together that we can say that it is a molecular compound. So we're going to call it, using the rules for molecular compounds, with the prefixes. So normally, when a single atom is at the beginning of a molecular compound, you don't have to put mono. You can dispense with putting the mono. So this is, you could call it monos phosphorus, but typically people will just say phosphorus pentafluoride. B is sodium iodide, and it's an ionic compound because sodium is on the left of the periodic table, and iodine is on the right. So one's a metal, and the other one's a non-metal. Anytime you get a metal with a non-metal, you can be pretty sure that's an ionic compound. So it's called sodium iodide. Sulfur with chlorine, they're pretty close in the periodic table, so I'm going to say it's molecular, and it's called sulfur dichloride. You use the prefixes. You only use the prefixes if you have a molecular compound. Don't use the prefixes if you're naming an ionic compound. So if the two things are far apart on the periodic table, do not use the prefixes. Okay? D. You have calcium, which is on the left side of the periodic table. It's a metal, and then a polyatomic ion nitrate with a -1 charge. So you're going to need two nitrates to combine with the calcium, so it's called calcium nitrate, and it's ionic. Iron chloride. I'm going to say this is an ionic compound. They are fairly far apart on the periodic table, although I bet you it's got a fair amount of molecular character because it's not so far apart. Anyway, it's called ferric chloride because the iron has a +3 charge and the chloride has a -1 charge. Lanthanum phosphide is compound F. Lanthanum is a metal. Phosphorus is a non-metal. So that's, to my way of thinking, that's an ionic compound. And lanthanum has a +3 charge because it's a group 3 element. Phosphorus takes on a -3 charge to form phosphide, so one of each will form lanthanum phosphide. G shows you cobalt carbonate. It's cobaltous, meaning it's got the lower charge of cobalt in it. There's only one cobalt atom and combined with one carbonate. Let me see what the original thumb says, though, before I do something wrong. Yeah, they show you CO3. So the cobalt, because it has to have a +2 charge to combine with carbonate, with a single carbonate molecule, and we know that the polyatomic anion carbonate has a -2 charge, it must mean that the cobalt has a +2 charge, which means it's the cobaltous version of the ion. There are two possibilities. Cobalt can form a +2 or a +3 charge. In this case, it's forming a +2 charge, so we're going to call it cobaltous carbonate. You put the OUS suffix on the metal when it's the lower charge of the two possibilities. If it had been cobalt with a +3 charge, we would have called it cobaltic carbonate, and then we would have had to put 3 carbonates and 2 cobaltics to make the compound. The last example is dinitrogen tetroxide, and just from the way I named it, you know that it's a molecular compound. And see, you use the prefixes. Di signifies 2, and tetro is for 4, or tetra is for 4, and then you drop the A, so it just becomes, you don't say tetraoxide, you drop the A, and you just leave one vowel. Putting 2 vowels together and pronouncing them usually sounds awkward. Next, no, that's it. We're done. 256 is done. And you should have this in your binders if you're in my class. Make sure that it's all done properly, and I will check it when we get together.